guys, welcome back to Biochemistry with Kary. Today we will be discussing the 1993 Nobel Prize-winning chemist Kary Mullis and his revolutionary contribution to the study of biochemistry and molecular diagnostics, the polymerase chain reaction or PCR technique, which is used to selectively amplify specific sequences of DNA in vitro. Kary Mullis was born December 28, 1944 in Lenoir, North Carolina and died August 7, 2019 in Newport Beach, California at the age of 74. In his 74 years, he spent the majority in academics and research. His academic career began in 1962 when he studied chemistry at the Georgia Institute of Technology. In 1966, he graduated with Bachelor's of Science and transferred to California, where he began his PhD in biochemistry at Berkeley. From 1973 to 77, he completed his postdoc fellowship at the University of Kansas in pulmonary and vascular health, before moving to UC San Francisco to extend his postdoc work in pharmaceutical chemistry until 1979. Following graduation, Mullis began as a researcher at the Cetus Corporation. It was here he discovered PCR in 1983. In 1986, Mullis assumed the role of director at Extronics Corporation and became consultant of nucleic acid chemistry until he retired from research in the 1990s to write. The idea for PCR came to Mullis one night in 1983 while stuck in a traffic jam. What if I use the natural replicating properties of DNA to exponentially increase copies of a target sequence, he thought to himself, but how exactly did he accomplish that? Well, Mullis designed an assay composed of 3 steps: denaturation, annealing, and elongation. During denaturation, the hydrogen bonds holding the double-stranded DNA together are broken by increasing the temperature to approximately 95 degrees, causing the template to separate into single strands. Once strands are separated, oligonucleotide fragments known as primers can anneal to the 3' end of the single-stranded DNA through hydrogen bonding. This is known as the annealing phase. Finally, to complete the process, a thermostable DNA polymerase known as Taq polymerase extends the primer in a 5' to 3' direction by adding dNTPs to the 3' end of the primer. Once this is complete, 2 new duplicates are formed, which are replicates of the original DNA template. We can now repeat the cycle with the newly formed DNA strands serving as templates for DNA amplification. With just 30 cycles, over 1 billion copies of the target sequence will be generated. The ability to produce increased quantities of a specified DNA segment effectively made the genetic blueprint identifiable, detectable, and testable. This made applications of PCR virtually endless to science. PCR is currently being applied in areas of genetic testing, forensic science, laboratory medicine, and many more. None of this would have been possible without the work of Kary Mullis. And that's it for today, folks. I'll see you next time on Biochemistry with Kary. Don't forget to like and subscribe.